All right, 15. Day 15, Cheetong. That's the Cheetong. Marine mollusks. Gumboot Cheetong. Alright. You've almost reached the exit of the cave, but the walls are getting closer together. Let's just cut to the important stuff. The shape is square. Quick scan gives us a risk level throughout the cave, so it's going to look like a bunch of integers, up to 9, I guess. You start in the top left, and your destination is the bottom right. Straightforward enough. Cannot move diagonally. This is just a Dijkstra problem right now, isn't it? So you add up the risk levels of each position you enter. Okay, so you can think of it like distance. There's no reason to ever backtrack. Find a path with lowest risk. What is the lowest total risk of any path from the top left to the bottom right? That is just Dijkstra. Should be linear time in the number of cells. All right, let's remind ourselves how to go Dijkstra. The number of times I've done breadth first search, depth first search, Dijkstra, A star, and I know I could have so easily just stored those programs so I never have to write them again. But it's good practice, isn't it? Okay, so let me just put some more coffee on. Alright, so yeah, it's just Dijkstra. I don't see any tricks to it, and it's nice small numbers. See, I was storing my coffee in a packet that I previously stored my marijuana in, so I think the coffee's gonna be a bit weedy. Alright, so it's the standard stuff for line in f dot read line grid dot strip. Do we want store it as ins? Yeah, might as well. Grid dot append. It'll be int x for x in line dot strip. All right, so that's the grid. We know it's square. Just say width. Width equals length of grid. And then we want to define dijkstra. So we're given a start, a goal, that's it. Let's get my coffee. All right. So, when you do Dijkstra, you want to do priority queue. What do we use for that? We use the thing called priority queue. Isn't there another one that people suggested that's maybe better? Oh no, that was for the queue data structure. Hello, Smab UK. Did I make it before the end this time? Yes, you did. I just starting problem 15. I just did 13 and 14 now. They were both interesting problems. 13 was the one about you have dots on a piece of paper and you're folding the paper like horizontally or vertically, and the dots like combine or whatever. Pretty easy to code. And then 14 was 14 was a good problem. It was where you had a polymer, which is a series of letters, and it has expansion rules. So every pair has a rule for a character that gets inserted between them, and you have to count what the massive chain would look like after 40 steps. So you need some sort of counter process because the number is too massive. Oh, like I've still got the results down there. Yeah, that's how many letters the final result has. Didn't take me long to code because I guess I've seen similar problems in the advent of code. He quite likes these polymer questions, doesn't he? We've had a few of them. So there are a couple of tricks that are often used. It's mostly just keeping track of the count of the pairs. And that's the only thing you ever keep track of. Because then that's just a fixed size counter. Yep, we're on to 15, which looks like just a basic Dijkstra warm-up. So, probably want a queue. How many times have we coded this before? Not as many as BFS or DFS, I suppose. We could even make it A star. I won't bother. It's gonna be fast enough on this grid. Q equals, and it probably won't be that effective either because the estimate will be like 1 for every step, but clearly this is like gonna be way more than 1 most of the time, so I don't think A star is even that good. Well, it'll be decent because it will still keep us going to the bottom right. Alright, so Q, priority Q, and then we want Q dot put start. So you start with the values. It's going to be 0. Start. Just check by solution. Definitely use Dijkstra. Yeah, I mean you can't really do it without Dijkstra. Like I'm sure people might have come up with their own solutions, which were really just Dijkstra that without like. They may have just basically invented Dijkstra from first principles, which is not too hard. But it may not use the same data structures and stuff. Yeah, I've written this so many times, and I could easily have just stored Dijkstra in a library somewhere, so I wouldn't have to write it so many times. But it's always good to just write it from scratch. Okay, what do we need? We need a visitor set. I suppose we actually want our visited start. No, you only visit things when you expand them. That's the general rule. And then while Q dot while not Q dot empty, we do current equals Q dot get. Now we have to. Now are we going to do lazy deletion here? Yes. Oh yeah, we need a distance, don't we? Then we don't need a visited set. Our current distance equals q.get. So in the queue, we've got a node, and we've got the distance that we've used to get to that. Now, in the meantime, before we pull this out, we may have found a better path to that location, in which case we have to lazily delete this. So we say, if d is less than dist current, that means that means this is obsolete. So we skip it. Wait, it's a priority queue, so why would that happen? Oh yeah, because we would have computed that one before, but the slower, the longer path to it is still stuck in the queue somewhere. We don't have a method of efficient deletion. I think you can use hash sets to do that, but okay, so we're working with the best path to this current. All right, if current is goal, I think we are immediately done. This absolutely must be the shortest path. So return D. We're gonna have to get neighbors. So for DI, DJ in. All right, if 0 is less or equal to neighbor I is less than width and it's a square, we'll just assume it's always a square. Okay, so that's get neighbors. So for neighbor in get neighbors current. Okay, so neighbor dist equals d plus 1. If no. D plus grid neighbor 0 neighbor 1. It's the value in the grid. Are there zeros in here? No. It would still work even if there were. If they were negative, then that's the problem. You can have cycles and stuff. Neighbor dist d, so current distance plus the distance to enter that cell. So if neighbor not in dist or dist, what we previously found is worse than neighbor dist, then we found a new best. So we update that. So we update the distance to the neighbor, whether or not we've seen it before. We pop it on the queue. So it will be neighbor dist neighbor. Is that everything? Yeah. And then if we reach this point, we shouldn't. But if we reach this point, it would mean we couldn't find a way to the goal. Leave that out for now. So let's just print Dijkstra from 0, 0 to I guess width -1, width -1. error 0. Just current 0? What? Oh, this is the wrong order. The current dist neighbor, yeah. We're out of range in the grid. So at some point we found a neighbor which was out of the grid. That shouldn't happen. Should be within these bounds. Because it's square, we don't have an issue with using the wrong axis. One 001. 01 was out of range. Neighbor grid. Oh, neighbor. What? Neighbor 1 is 1. Grid. Let me just print the grid, make sure I haven't kind of made it all wrong. Oh my god, what happened here? What? F.read line. I missed an S. F.read lines. 462. Correct. Now that you know how to find low-risk paths in the cave, you can try to find your way out. The entire cave is actually 5 times larger in both dimensions than you thought. The area you originally scanned is just one tile in a 5x5 tile area that forms the full map. The original map tile repeats to the right. It's a subtle bug, yeah, the most subtle of bugs. Like, usually I print my grid to start with just to make sure I've done it right. Full map. Your original map tile repeats to the right and downward. Each time the tile repeats to the right or downward, all of its risk levels are 1 higher than the tile immediately up or left of it. However, risk levels above 9 wrap back around to 1. So we can just build the full grid that's 5 times bigger. It's not going to be crazy big. Or, alternatively, we just have a function that returns what a location should be. And it's not too hard to compute that, isn't it? We just do an integer division of the row size, blah, 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 add that, and modulus. So it's just Dijkstra in a bigger map. Fine. Well, because the Dijkstra is already coded to a hard-coded grid, we could just make the grid. Like, how big is it going to be? 100, so it's going to go to 500 by 500. That's fine. And the runtime would be linear in that number anyway, even if we didn't build the whole grid. So we might as well just do it. So we'll need a new getNeighbors method as well. Or we just say for a given width. Try and avoid any carrying forward any bugs. We'll just make a new getNeighbors. Dijkstra will be the same. Alright, it's actually better if we just supply a width. Or the grid. The width will be fine. Supply a grid, because we actually will supply... Yeah, actually this actually does make sense. Because then you can just say getNeighbors current grid dot the grid length of grid. So we're supplying the grid, and yeah, get rid of this. And then getNeighbors, it's gonna be, there we go. And then get rid of width. All right, getNeighbors width. Okay, and then Dijkstra uses a grid. And then here be make sure we still get the same result. 462. We should, yeah, okay. Okay, so now we just expand the grid and then plug it back into Dijkstra. Bigger grid. Just so that we don't have to keep calling that. Bigger grid. It's gonna be, so it'll be, let's say none for 5 times width. 5 times width. Or we can even say bigger width equals, okay, big width. Big width, big grid equals 5 times width. Big grid equals that for I in range. Big width for j in range. Big width so we want to know which phase we're in each. What did they say again? So it's repeats to the right and downward. Each time the tile repeats to the right or downward, all of its risk levels are 1 higher. So it's basically the number of phases to the right plus the number of phases downwards is the number of levels higher you go. Okay. So num tiles, I don't know a better description, but num horizontal tile equals start with the vert equals I divided by little width. So it'll be 0 for the first one and so on. Okay. J divided by width. So the value equals, so it's going to be grid, going to be I, but modulo out all those widths. So it'll be the value that's in the original grid plus hang on, so it doesn't wrap around back to 0, it wraps around back to 1. So what we actually want to do is so you sort of you minus 1 and then you do modulo 9 and then you add 1 back. Either that or you just divide by the number of, yeah, I think the easiest way to write it is just so it's going to be, so we minus 1, so that it's now a number from 0 to 8, and 9 means it goes back to 0. Right? Then we plus that and plus that. That's how many times it increases. So that number we want to modulo 9. So it goes back to a range between 0 and 8. And then finally add the 1 back on to bring it back into the 1 to 9 range. Yeah, I think. All right, value. That's the value of this one. So basically, big grid I j equals value. So we've stored all the values now. We don't have to do it on the fly. And now we just do this, right? We 0, 0. Big. Oh, okay, that was quick. 2, 8, 4, 6. Could try throwing an A star in, but maybe probably can't be bothered. Correct. Yeah. I mean, if it works. If I was rewriting this bit of code, I would refactor into methods to explain what it does better. Looks weird reading it now. I could try throwing A star in, but then how much work do we have to do? It's just... it's not interesting. It might be faster, but we'll save it for a time when we actually need that speed. Well, that went quicker than expected, so I could actually squeeze another problem in. I'll take a peek at the next problem.